Hello, I'm Isaac, and this is video 1 in a 3-video series about center of mass. We're going to start out with centers of mass in one dimension for a particle system. And what that means is that we have a bunch of points that have a certain mass, and we're trying to figure out if all those points are connected along one axis, one lever. We're trying to figure out where would we put the fulcrum to balance that lever. And so I've got drawn up here our lever, which is along the x-axis, and several masses. I have mass 1, mass 2, all the way up to the nth mass. Okay, so n could be any number. This equation will end up working for any number of particles. So we're going to call the last mass the nth mass. Um, and as you can see here, we have different distances that these masses are away from the x equals 0 line, or the origin of our x-axis. So we have x1, which is the measure to m1, x2, which is the measure to m2, and xn, which is the measure to mn. And also we have forces caused by these masses. We're assuming this is happening on Earth, which means that our forces are going to equal ma. So F1 is going to equal mass 1 times the acceleration on Earth, which is g. F2 is going to be mass 2 times g. They're both on Earth, so they both get gravitational acceleration. And Fn is going to equal the mass n, the nth mass, times gravity as well. So the first step here is we're going to go ahead and assume the axiom that for a static system, so in other words, we want this thing to balance, which means it shouldn't move when we're all good and done. So the sum of torques in that static system has to equal 0. And that is an axiom, so that's kind of the basis of this whole thing. It can be proven experimentally, but there is no proof that will tell you that sum of torques equals 0 for static system, at least none that I know of. So we're going to write our first equation. If sum of torques equals 0, well then we would say that we're going to add the torque caused by F1 plus the torque caused by F2 plus the torque caused by Fn ought to equal 0. And for a torque is equal to R cross F, R being the distance from the rotation point, and F being the force, like for example F1 or F2. And then the cross product kind of means to take R times F and then times the sine of the angle theta between them. Now I've oriented this lever to be parallel with the ground, and so what we're going to do is go ahead and draw right angles here. So all of those angles from the force to the lever are going to be 90-degree angles, which means the sine of 90 degrees is equal to 1. So we've now simplified torques equal to the distance from the rotation point, which in our case is the x distance. So xi, I stands for the index, so that could be x1, x2, or xn. And then we're going to multiply that by the force of the ith iteration, so that could be force 1, force 2, force n. And to simplify that even further, because we know that force equals ma, we can say that the force here is equal to the mass, so the ith mass, times the acceleration on Earth, which is always g. And so now we have this simplified expression to help us find what torques are being caused by these forces. So torque 1 is caused by force 1 at a distance 1. So torque 1 is going to equal x1 times F1, which happens to equal m1 times g. m1 times g plus torque 2, which is x2 times m2 times g, plus the nth torque caused by the nth force and the nth mass, which is going to equal xn times mn times g. So now we have our equation here. and that's going to equal 0 because in a static system, in equilibrium, the sum of torques is going to equal 0. So that's the first equation of this proof. The next equation is we're going to imagine that we're taking all of the masses. So I'm going to draw another axis here, x-axis right here, and we're going to find a place to put all the masses added together. So we're going to put all the masses together and put them at a certain distance, and we're going to call that distance x bar, and x bar is typically used to denote, in physics, the center of mass. And so that's x bar away from the x equals 0 line. And the mass of this is the mass of all three of these added up. So the mass here is now m1 plus m2 plus the nth mass. So we've scrunched all of these together into one spot, and it's x bar distance away from the x-axis. So now we're going to write another sum of torques. We're going to say the sum of torques equals 0, which equals, well, there's a force caused by these masses. We'll just call it F. And it's, once again, we oriented the lever to where it's going to be at 90 degrees from the force, which is also parallel. The lever is parallel with the ground. So we have a 90-degree angle, which means we can use our nice torque formula there. So this time we only have one torque, and that torque is equal to x bar times F. And in this case, F equals mass times acceleration, as usual. Still have g acceleration. So force is going to equal the masses, m1 plus m2 plus mn, times the acceleration. And we got to make sure to put those in brackets because we're adding up all the masses before we times them by the acceleration. So rewriting that down here, we have x bar times m1 plus m2 plus the nth mass times g, and all of that still equals 0 because we're looking for static equilibrium. We can now divide out gravity from both sides. It's going to cancel there, and this is just going to go to 0 because 0 divided by anything is just 0. Alright, so now we have two equations. Up here I'm also going to divide out. On our first equation I'm going to divide g out of both sides. And once again, 0 divided by anything is 0, and then all the g's cancel out here. So if this equation equals 0 and this equation equals 0, we should be able to set them equal to each other. So that's what I'm going to go ahead and do right here. So here's this equation, x bar times m1 plus m2 all the way to the nth mass. First equation is equal to second equation, which is x1 m1 plus x2 m2 plus xn times the nth mass. Alright, so here's our equation, and we are going to go ahead and divide and get x bar all on its own, because that's what we're trying to solve for, is the center of mass. And so you can see here, if I divide both sides by the sum of masses on the left-hand side, that'll cancel. Divided by the sum of masses on the left hand. Alright, so now we've went ahead and solved for x bar. It equals x1 m1 plus x2 m2 plus the nth distance to the nth mass divided by all the masses summed. Up to mn. I'm sorry, I wrote that as m3. It's the nth mass. Alright. Now there's a little more of a compact way to write this. I'm going to go ahead and erase some of the upper board here to make room for it. So we can write this in what's called summation notation, which means that if you look at this equation, there's a pattern to it. It looks like we're adding x1m1 plus x2m2 plus xn plus mn, and then dividing it by m1 plus m2 plus mn. Well, we like to write this using index notation because it seems like the 1's are always paired with the 1's, the 2's with the 2's, and it's always divided by the sum of all the masses. So summation notation says that I can write this as x bar equals uppercase sigma, which means the sum of, kind of like we did earlier with sum of torques, sum of the mass, the ith mass, the whatever iteration of mass that is, times xi. So mass 1 plus x times x1, mass 2 times x2, that's what this top part is taking care of. And then we're going to divide it by what's on the bottom, which happens to, it seems to be, it's the sum of the masses, to whatever number of masses you have. And so we're dividing by the sum of mi. And so this right here is your equations for center of mass of a particle system in 1 dimensions. This can be extrapolated to y bar. It'll just be the sum of mi, yi divided by the sum of mi, and so on for any axis that you choose that's Cartesian. And so I hope you enjoyed this video, and hopefully it was helpful. Have a great day.